Okay, hello everyone. Today we will learn about the chapter 8 estimation. The chapter 8.1 is introduction to estimation. So the populations are characterized by numerical descriptive measures called parameters. For example, for a population mean, probably we can say this is a population, and population mean we use mu to characterize the characteristics of this population. Okay, and an estimation is about how we estimate those parameters. So we say there is a population and there is population mean mu, and we want to estimate the population mean parameter, and that's estimator. So for example, sample mean is an estimator of population mean mu. So we can define our estimator y bar as this, and this is an estimator to estimate the population mean mu. And in this case, it's actually unbiased estimator, and we will learn it later. So because the expected value of y bar is equal to mu, and so in this case, we can call it unbiased estimator. For definition 8.1, an estimator is a rule, often expressed as a formula that tells how to calculate the value of an estimate based on the measurement contained in a sample. So estimator is a function of samples. So y bar, for example, sample mean y bar is function of samples. So this is sum of all average of all samples is one possible point estimator of population mean mu. And since y bar is a function of samples, it's also again random variable. Y bar is also a random variable, and and actually, there might be many other estimators rather than y bar. Probably we can just use yi. We can just y1. We can just take just the first sample and say that this is my estimate. That's also an estimator. So there might be many other estimators, but which estimator would be better? So how we can compare each estimators? That's what we will tell in the following chapters. In chapter 8.2, we are going to learn how we can compare estimators, which are the bias and mean square error of point estimators. So we were going to learn bias and MSE, mean square error. So here is just for a notation. We will call theta a population parameter, and the estimator theta will be indicated by the symbol theta hat. Okay, this is just notation. And point estimator that satisfies, actually this is expected value of estimator theta hat equals theta from the above notation. And this is an example of the unbiased estimator. So if our point estimator that satisfies expected value of theta hat equals theta are said to be unbiased. In this case, we tell that our estimator is unbiased. So what's this situation? So here, the figure 8.1 describes a distribution of estimates. So here's the true theta. We assume that our true parameter theta is a fixed point. So this is, for example, this is a mean mu, which is fixed. So we have a population, and there is a population mean parameter, which is a fixed value. And our estimate theta hat is y bar, and the y bar is function of our samples, so it varies. So every time we sample 10 points, say y bar is average value of 10 sample points, x1 to x10, average value from 10 sample points. Every time we sample 10 samples, every time we have different y bar value. And so the distribution of y bar, it will probably shaped like this, bell shaped. And so yeah, so the figure 8.1, this is describes a distribution of our estimate. And in figure 8.2, sometimes our estimate um, have uh, have distribution like this. So let's say our zeta hat, the distribution of our estimator is something like this. And in this case, the expected value of zeta hat would be this point. If our zeta hat, the distribution of our zeta hat is like this, then the expected value of zeta hat would be this point. And in this case, if the true zeta is here, then expected value of zeta hat is not equal to zeta. So in this case, we say the estimator is biased, a positively biased estimator. Uh, Here is definition 8.2 and 8.3. Let zeta hat be a point estimator for a parameter zeta. Then zeta hat is an unbiased estimator if expected value of zeta hat is equal to zeta. If expected value of zeta hat is not equal to zeta, then zeta hat is said to be biased. Okay. And the bias of a point estimator zeta hat is given by this. So this is the definition of bias term. So we define the bias of our zeta hat is equal to expected value of zeta hat minus zeta. So this is definition for the bias term. Um, mm, Okay, from here, for an example, again, let's say we have population, and here mu is the sample mean parameter for sample mean. And if our zeta hat is y bar, then the expected value of y bar, this is before we do that, let's say for all yi's, y1 to yn, or for all samples, they are independent samples, and the expected value of each yi equals mu. If we have this assumption, then expected value of y bar is again mu. And so in this case, we say that our estimator y bar is an unbiased estimator. Okay. To characterize the goodness of estimator, we use mean square error, MSE. Previously, we learned the bias. The one good characteristic for good estimator would be unbiased estimator, or the one that have small bias. And the bias term is expected value of zeta hat minus zeta. Would this enough? Would this enough? This be enough for good estimator? Since I questioning to you, probably there's another concept which is variance. So let's say let's say our estimator, the distribution of our estimator, this is true zeta, and one of the distribution of our estimator, one thing is like this, and the mean of our zeta hat would be positioned in here, and here's the other estimator. So in this estimator, the okay, so this is the distribution for another zeta hat 2, distribution for zeta hat 2, and actually this is unbiased estimator. Expected value of zeta hat 2 is zeta. which estimator would be good? So here, this is estimator for theta, and this is theta 1 hat, and this is theta 2 hat. Distribution for theta 1 hat is slightly biased, but it usually theta 1 hat is close to theta. So it's however, for theta hat 2, most of times it's smaller than theta or sometimes greater than theta, but on average, expected value of theta 2 hat is theta. Which one is better? In unbiased concept, this one is unbiased, but this is not better than the first one in mean square error concepts. Um, Here we have mean square error concept. We want our estimator have a lower bias, and also we want the variance of our estimator as small as possible. So this is our estimator term, which is expected value of theta hat minus theta squared. In here, what we want is we want to we want our theta hat as close to theta as possible. We want to theta hat and theta as close as possible. Okay, so this is our goal inside of the mean square error concept. Previously, we discussed about the good goodness of the estimators. So and one of the criteria is variance, and also the other term is bias term. So we want to minimize both the variance and bias. And actually, the MSE, the criteria for minimizing mean square error, is actually considering both variance term and bias term. MSE can be expressed as a function of both its variance and its bias. So here's our MSE, and if we prove it, this term here, so far this is the definition, and this term can be expressed as variance term plus bias squared term. Okay, let's try to solve it. So this part can be expressed as this: expected value of theta hat minus expected value of theta hat and plus expected value of theta hat minus theta squared. Okay, so we plus and minus expected value of theta hat, and then we group these two together and express the square term. Then this one becomes expected value of theta hat minus expected value of theta hat squared plus 2 times theta hat minus expected value of theta hat times expected value of theta hat minus theta, and plus expected value of theta hat minus theta squared. Okay. And in this notation, actually, the expectation goes inside for each term. So expect this one is expected value of theta hat minus expected value of theta hat squared, and plus 2 times expected value of theta hat minus expected value of theta hat and expected value of theta hat minus theta, plus expected value of theta hat minus zeta squared. Okay. Somewhat confusing. And here this expectation goes to 0. Why is it true? And actually this part is constant. Expected value of zeta hat minus zeta. This value is constant. So it can go out to the expectation, and so it's 2 times expected value of zeta hat minus zeta, and expected value of zeta hat minus expected value of zeta hat. And in this part, this one is again constant. So expected value of constant is constant, and expected value of zeta hat, this part is expected value of zeta hat. And so expected value of zeta hat minus expected value of zeta hat, this one cancelled out, and this becomes 0. So this term goes away, and what's the first term and the last term? The first term is actually the variance of zeta hat. This, by definition, this is variance of zeta hat. And also the last term, this one is the definition of bias. So this one is bias squared. And actually, these two values are constant. So expected value of constant is constant. So this expectation part goes away. And so this is just bias zeta hat square. Okay, so this is the proof for the why the mean square error of zeta hat is sum of variance term plus bias squared term. And so the minimizing mean square error implies that we want to minimize both the variance and the bias. Okay. Okay, let's try to solve exercise problem 8.3. Suppose that zeta hat is an estimator for a parameter theta, and expected value of zeta hat is a zeta plus b for some non-zero constant a and b. In terms of a, b, and theta, what is bias term? The bias of zeta hat. Bias of zeta hat is expected value of zeta hat minus zeta. So this is definition of the bias term, and expected value of zeta hat is a zeta minus b. And so this is our answer. The bias of the zeta is actually, we can write it, any solution would be fine. A minus 1 zeta minus b. Okay, and what is b? Find a function of zeta hat. So say zeta star is a function of zeta hat, and we want this to be unbiased estimator. We want this. We have this. What we want is we want expected value of zeta star is actually equals zeta. And actually to make it like this, in expected value of zeta hat, if we minus b and divide by a, then it would be theta. So the one function would be if we define it as zeta hat minus b divided by a, then I think it would be unbiased estimator. So let's try. So expected value of zeta hat star is expected value of a zeta hat minus b, and the expected value of zeta hat is expected value of zeta hat is uh, a zeta plus b minus b divided by a. This cancelled, and also a part cancelled, and so this is a. So um, so zeta hat star is unbiased. So if we define our zeta hat to be like this, then it is unbiased. Okay. And let's move on to example 8.8. Suppose that y1, y2, and y3 denote a random sample from an exponential distribution with density function here, exponential with parameter zeta, and consider the following 5 estimators of zeta. Zeta 1 hat is for first sample y1. Zeta 2 hat is equal to y1 plus y2 divided by 2. Y3 hat is y1 plus 2y2 divided by 3. And y4 hat is minimum of y1, y2, and y3. And hat 5 is y bar. And okay, which of these estimators are unbiased? So we want to calculate expected value of each estimators, and expected value of zeta 1 hat is expected value of y1, and since y1 follows exponential distribution with the parameter zeta, so this is zeta. So this is unbiased. And what about expected value of zeta hat 2? And its expected value of 2 y1 plus y2. And this is 2 expected value of y1, which is zeta, and expected value of y2 is zeta. And so this is again zeta. And what about expected value of zeta hat 3? And similarly, actually, you can calculate this as zeta, and also expected value of zeta hat 5. This one is expected value of y bar, and also you can prove that this one is zeta. Okay, so the first, second, third, and fifth one are unbiased estimators. And what about this? And to calculate the expected value of zeta hat 4, you need to find the density of the minimum of y1, y2, and y3. Okay. So we want to calculate the expected value of zeta hat 4, and to calculate the expected value of zeta hat 4, we need to derive the distribution of zeta hat 4. And actually, you can use the theorem 6.5 that we've learned from order statistic part, but at here to remind of, I'd like to derive it. Okay, let's define this minimum of y1 to y3 as z, or we can write it as y1, and we want to find the distribution function for this thing, and to do that, this is probability of z, which is y1, minimum of y1 to y3. This is less than small z, and we can write it as 1 minus probability of y1 is greater than z. And actually, the minimum of y1, y2, y3 is greater than z. What's that implies? So here's y1, y2, y3. Let's say there are y1, y2, and y3, and minimum is this thing. And if minimum is greater than z, so z is here. If minimum of these is greater than z, what this implies is that y1 is greater than z, and y2 is greater than z, and y3 is greater than z. So minimum of y1 and y2 and y3 is greater than z implies this thing. And actually, since y1 and y2 and y3 are independent, we can write it as y1 is greater than z to the third, and and this is 1 minus density function for y, 1 minus wait a minute, 1 minus density function of y to third. And if we differentiate each side, then we can get fz of z is equal to 3 times 1 minus f y y to the second and f y y. Okay, and actually you can get the exactly same thing by applying theorem 6.5. So check the theorem 6.5, and you can get this one by using order statistic. So f1 using theorem 6.5, g1 y1 is equal to this thing. Okay, and let's go ahead. So here fy y y is integration of okay, let's calculate 1 minus fy y. So this is from y to infinity, because this thing is probability of y is greater than small y, and so this is less than e to the minus y over theta dy, and this is minus e to the minus y over theta from y to infinity, and this is e to the minus y over theta. So we can put this thing here, and so this is 3 times e to the minus y over theta to second, and 1 over theta e to the minus y over theta. And so this is 3 over theta e to the minus 3y over theta. And actually we can rewrite this as 1 over theta over 3 e to the minus y over theta over 3. And then you can know that this z follows exponential distribution theta over 3. So actually z is y1, and so the expected value of z is equal to theta over 3. And so this is unbiased estimator for theta. A biased estimator for theta. Biased. Okay. Now let's move to question B. Among the unbiased estimators, which has the smallest variance? We proved that this one is biased estimator, and these are unbiased estimators. And so we want to find the one who have smallest variance. So the variance of theta 1 hat is variance of y1, and this is theta. The variance For when we have exponential distribution, the variance is zeta. And what about variance of zeta at 2? And this one is variance of 1 over 2y1 plus 1 over 2y2. So it is 1 over 4 zeta plus 1 over 4 zeta. And so it is 1 over 2 zeta. And variance for zeta 3 is variance of 1 over 3 y1 plus 2 over 3 y2, and so this is 1 over 9 zeta plus 4 over 9 zeta, which is 5 over 9 zeta. And what about variance of y bar, which is variance of 1 over 3 y1 plus 1 over 3, y2 plus 1 over 3, y3. So this is 1 over 9 zeta plus 1 over 9 zeta plus 1 over 9 zeta, which is 1 over 3 zeta. And as you can see, the variance, this one is the smallest. So we have proved that this one have the smallest variance, and since you know that the one have a smaller variance, that's the better estimator. So set y bar is the best estimators among these candidates. Okay. Homework for chapter 8.2 are these. In chapter 8.3, we will talk about some common unbiased point estimators. And actually, the ones described here, they used a lot, so it's worth you know. So for the target parameter mu, we use point estimator as y bar. So if you calculate n number of samples and to estimate the target parameter, the population mean, then you use y bar as your point estimator. And as we learned, the expected value of y bar is mu, and also the standard error, which is square root of variance of estimator, and variance of y bar, if yi expected value of yi equals mu, and variance of yi equals sigma square, and then variance of y bar is sigma square over n. Why is it true? Why is it true? The variance of y bar is 1 over n y1 plus dot 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 1 over n yn, and so this is 1 over n square sigma square 1 over n square plus dot 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 n square sigma square, and we have n number of this, so this is sigma square over n. And since the variance of y bar is sigma square over n, standard error is square root of it. So square root of sigma square over n is this term. So we have showed this, and for the p, the ratio parameter, how the percentage of people who favors candidate Jones, something like that. The p hat is actually y divided by n. And here the y, actually this is also some of Bernoulli trials, BIs. In this case, y equals Bernoulli trial, BI. For each BI follows Bernoulli distribution, Bernoulli a distribution with parameter p, and so the sum of bi's y follows binomial distribution, and p. So um, if y follows binomial distribution, expected value of y is np, and p hat is y divided by n. So the expected value of y over n is p. And also the variance of y over n, um, this is n square. Variance of y is npq, npq divided by n square. So it's pq divided by n, and so if we take square root, we get this as our standard error. Okay, and when we are comparing population mean, we have two populations, population 1 and population 2. Many times we want to compare the mean parameter of two populations. In that case, we use y1 hat minus y2, y1 bar minus y2 bar to compare the difference between two population mean. And in this case, the expected value would be easy, mu1 minus mu2, and the variance of these, actually variance part is also easy. Variance of y1 bar minus y2 bar is actually variance of y1 bar plus variance of y2 bar, and this is actually this is same, sigma square over n1 plus sigma square over n2. And actually here we assumed that the variance of population 1 and 2 are same. We have equivariance, then in this case the derivation is easy. So since the variance is this, take square root term to get this variance. And similarly, you can also get the variance term for the p case. So similarly, we can calculate this. Derivations are very similar, and the one thing that one thing to note is that these are happen very commonly. They are probably you are going to see these situation in your real life many times. So they are some common unbiased point estimators that probably you will use in the future. Okay. Okay, let's move on to example 8.1. Let y1, y2, and yn be a random sample with expected value of yi equals mu and variance of yi equals sigma square. Show that this is biased estimator for sigma square, and this is an unbiased estimator for sigma square. The difference of these two, the multiplicating constant is 1 over n or 1 over n minus 1. And actually, if we use 1 over n minus 1, then it is unbiased estimator for sigma square. Okay, so let's prove it. Why is it? How to show that it is unbiased estimator? By definition, expected value of s square equals sigma square. In this case, this is unbiased estimator. And to prove that, actually it is just calculating expected value of this part, since 1 over n minus 1 is just constant term. So the important part is expected value of this part. So what is this part? Expected value of sigma is 1 to n yi squared minus 2 yi y bar minus y bar squared. And from here we move summations inside. So sum of yi squared minus 2 actually from sum of yi times y bar, since y bar is constant from in the integral, we put y bar outside, and sum of yi minus y bar, sum of I equals 1 to n y bar squared, y bar, oh no, y bar squared. And from here, actually y bar is constant in this integration, so it is n times y bar, and from here this part is actually sum of yi divided by n is y bar, so this one is n times y bar, so this is 2n times y bar squared. Oh, and also this part is n times y bar squared, and this part is plus. Okay, so then this part is expected value of sum of y I squared minus n times y bar squared, and so this one becomes sum of expected value of yi square minus n times expected value of y bar square. Okay, so let's try to solve this. Previously we have shown that this term becomes this, and from here before we move on, what we know is that variance of y is sigma square, and this one is expected value of y square minus e y square, and which is mu. So expected value of y square minus mu square. And also, what is variance of y bar? It's sigma square over n. And also, this is expected value of y bar square minus expected value of y bar square. And this is expected value of y bar square minus mu square. Okay, then let's plug in these from here. Sum of I equals 1 to n, expected value of yi square is sigma square plus mu square, so sigma square plus mu square, and minus n times expected value of y bar square. It is n over sigma square plus mu square. Okay, and so we have n number of sigma square plus n number of mu square minus sigma square minus n mu square. So these two terms cancelled, and this becomes n minus 1 sigma square. And so if we define our s square as 1 over n minus 1 times sum of I equals 1 to n yi minus y bar squared, then the expected value of s square is the expected value of this thing. Since expected value of this thing is n minus 1 times sigma square, this term becomes sigma square. So expected value of s square is equal to sigma square. Okay.